Hello, this is a video showing how factors work in R and how to fit one-factor regression models in R. So to do that, we're going to be looking at a data set of measurements of the speed of light, and I'll briefly explain what's going on here. But let's read in the data first. So it's in a file called speedoflight.csv. And if you look at the data, it has two columns. There's a velocity measurement, the units aren't given, and then there's a trial number. So what we're going to be doing in this video is we're going to be looking at modeling the velocity as a function of the trial number. And I will say a little bit more about what this means. Okay, so to make our life easier, let's just define the variable called velocity. That's going to be our response. N is the total number of observations. And then the trial name is this trial variable. So if we were to print that out, we get this. So R will read this column in to a data frame that I've named data. And we're going to look at what type of variable this trial name thing is. So if you want to figure out what the type of a vector or an object are, you can call the class function. So in this version of R, it reads the this string column in the comma-separated value file, CSV file, as a character. So the class down here is character. Now this isn't true for earlier versions of R. So in earlier versions of R, before version 4, it would read in columns that are strings. It would read them in as factors automatically. And lots of people didn't like that default behavior. So eventually R changed it. So now it just treats it as a character. If you're in an earlier version of R, so I have R version 4.0.3, I believe. Let me double check that. Yeah, 4.0.3. If you're in an R version that's before version 4, so version 3 point something, you can add an additional argument here, as.is equals true, and it will have the same behavior. If you don't have this and you're in an early version of R, it will treat that trial column as a factor. Okay. So in this version, it's a character. One additional way to get more information about a variable in R is to use the str function. So this says it's a character. It has 100 entries. So here n is 100, and then it prints out the first few values. There's a handy function called is.numeric. So this will give a true false or whether or not it's numeric. So it's not, so it's false. And then there's corresponding is.dot functions for different classes. So is.factor is false. So I'm going to create a new vector that treats this trial variable as a factor. And the function for converting to a factor is as.factor. And then there are corresponding functions for like as.numeric, as.character as well. So I'm going to call trialfac as.factor of trial name. So I can print that out. Oops. I need to do this mapping. Again, I'm using the Vim key bindings. And I like this shortcut JK to get out of insert mode. Okay, so trialfac, we can see that R is treating this as a factor because it lists out the levels. So there are 5 different levels of the trial, and first, second, third, fourth, and fifth. Okay, so if you're in past R version 4.0, this line should give you an error. So it's trying to plot a numeric response against a character. And so R doesn't know what to do with that. But it does know what to do if you make the horizontal axis the factor variable. So what it does by default is it takes these levels and puts them on the horizontal axis, and then makes a box plot for the data from each of the levels. So this is the default behavior when you put in a factor as the x variable. So one thing you'll notice is that R just orders them alphabetically. So R doesn't know that first comes before fifth. It just does alphabetical ordering. So it does fifth, first, fourth, second, third, which is probably not what we want. So I'm going to create a new variable called trial num. So the way I'm going to create this is I'm going to initialize it with NAs. So trial num is just NAs. And then I'm going to go through first, second, third, fourth, and fifth. And I'm going to check for all the entries for which trial name is first, I'm going to assign a 1. And then for second, I'm going to assign a 2, 3, 4, and 5. So this is going to be a numeric because I've assigned numeric values here, 1, 2, 3, 4, or 5. So class of trial num is numeric, and of course is.numeric will return true, and this is no longer a factor, so it's false. Okay, so that's the trial num. I just converted those characters to numbers based on my knowledge of what the word first means. So if I plot this again with trial num on the horizontal axis, I'm going to get this. Now I want to add the axes back myself, so I'm going to use the axis function. So on the axis 1 is the first axis. At the trial numbers 1 through 5, I'm going to put these 5 labels. So that does that. And then I'm going to do a vertical axis, and then I'm going to draw a box. So this is another way to plot the data where I'm plotting the individual points here. So I like this better than the box plot, but I still don't quite like this plot because the response values are actually discrete. So when you're plotting, you have these 5 discrete values of the horizontal axis, but then also the response values are rounded to integers. And so what you get is 2 of the dots or circles will be plotted on top of each other in many cases. So you can kind of see that R makes the lines a little bit thicker, but when they're over plotted. But that's not really ideal. Someone looking at this wouldn't know that there's an extra circle there. So one thing I like to do when I'm plotting a numeric response against factor levels is I will take these horizontal values 1, 2, 3, 4, and 5 and kind of jitter them in the horizontal direction so that you're unlikely to get 2 points directly on top of each other. So that's what I'm going to do here. So instead of just plotting trial num, I'm going to add a small amount of a normal random variable to each of them and then keep the vertical axis the same. So if you see what happens here, you get this plot. So you still sometimes get points that are very close to each other, but now actually here you get these 2 that are very close. So if you don't like it, you can just redo it until you get one that you like. Okay, that one's pretty good. So now it's clear that there are multiple observations. There are actually 3 here with the same vertical velocity value. So I like this plot a lot better. It's maybe slightly messier, but it doesn't conceal any information about the data. You can see exactly what's happening here. So I much prefer this to a box plot. My general advice about box plots is to, if you find yourself making a box plot, you should really think twice about it and think about whether you can represent the data in a different way. So I think this contains a lot more information about the data than that original box plot did. All right, so this method of creating this horizontal axis was a little bit clunky because I had to kind of loop through all of them and make these assignments. So what I'm going to do is I'm going to show you a little bit cleaner way to reorder the levels of the factors. So if there's a function called levels. So if I put in a factor vector here as the argument to the levels function, this will print out what the levels of the factor are. And importantly, it's going to print them out in the order that R has stored them in. Let's see. Actually, let me show you one more thing. So R does it alphabetically, so it puts fifth first. What R's really doing under the hood with factors is it's assigning an integer to each variable. And the way you kind of see what integer gets assigned is if you convert a factor back to numeric. So if I do as.numeric of trial fac, this will reveal what integer it assigned to each level of the factor. So this is our trial fac is all our data, and it's listed. This is trial 1. This is trial 2. So it assigned number 4 to the second trial, 5 to third trial, 3 to fourth trial, and 1 to fifth trial. So the 1 to fifth trial, you can see it did it alphabetically. So these 1s correspond to the fifth trial, and that's because fifth is the first level of the factor. These 2s corresponds to the first trial, and that's because first was second alphabetically. So there's a couple ways to see what R is doing here. All right, so I don't like that. I don't like that fifth is before first. So I'm going to try to remedy that. One way of doing it, there's a function in R called relevel. So the way relevel works is the first argument is your factor variable or vector. And then the second argument is which level you want to make the baseline level or the first level. And so I'm going to make first the first level or the base level. And I'm going to assign that to a new vector called trial fac 2. So let's look at trial fac 2. So now it lists first. But it just kind of kept everything else in the same order otherwise. So what we really want to do is order them first, second, third, fourth, fifth. That would make the most sense. And to do that, we can use a function called factor. So let's look at the documentation for factor. All right, so the function factor is used to encode a vector with a factor, encode a vector as a factor. If the argument ordered is true, the factor levels are assumed to be ordered. For compatibility with S, there is also a function ordered. So here's how it gets used. So the first argument is your variable, so the vector, so trial name we're going to put in. And the second argument are the levels in the order you want them to be. And then we'll ignore the rest of them for now. So I'm going to create this variable called trial fac ordered. The first argument is trial name, and then the second argument are the levels in the order that I want them. In particular, I'm going to do first, second, third, fourth, and fifth. So if I run this, and then I look at them, now they're ordered the right way. So first, second, third, fourth, fifth, and then the levels are ordered this way. And then if I were to call the plot function with trial fac ordered as the first argument, it's going to make the box plots, but it's going to put them in the right order. So first, second, third, fourth, and fifth. So again, I don't love the box plot, but if you have to make a box plot and you want to get them in the right order or in the order that you prefer, you can create a new factor using the factor function and specify the ordering that you want. All right, so let's that's some general ideas about dealing with factor variables in R. Let's look at the data and let's fit some models to them. So let me go back and put the plot up that I like, which was this one. So this is an experiment for measuring the speed of light. And I don't remember who created this data set. I've been teaching with this for a while. But it comes from a common experimental method for measuring the speed of light one of the earliest methods. And the way it works is you have a mirror that you start spinning really fast, and then you shine a beam of light at the mirror, and if the mirror is spinning fast enough, the light that gets that bounces off the mirror will get deflected at an angle, and by measuring that angle, you can get a measurement of what the speed of light is. So I'm not going to go into any more detail than that, but that's where the data come from. And the way this particular experiment worked is they started spinning up the mirror, and then they turned the light on, and they'd get a measurement, and then they would turn the light off, and they get another measurement, and they'd repeat that 5 times. And then they'd stop spinning the mirror, and then they'd start it back up and then repeat. So this trial number 1 corresponds to the first measurement they make after they start spinning up the mirror, and then they take 5 more measurements before they shut it down. So one thing you might be interested in is, are there significant differences among these 5 measurements per time that they spin up the mirror? And it looks like maybe there is. So it looks like the data from the first measurement looks different from the data from the other measurements. First of all, there's more spread in the vertical direction. It has both one of the lowest measurements and one of the highest measurements. And it also looks like the average is maybe a little bit higher than the other ones. So that's what we're going to investigate. We're going to investigate whether the averages are different among these 5 trials. And we're going to expect to find that there's something different about the first trial, but maybe not big differences among the last 4 trials. All right, so that's a good idea to look at the data and try to sort of guess what the outcome of the analysis is going to be. So then if you see something that's like wildly different, you can go back and check to see if you've made a mistake somewhere. Okay, so we're going to be comparing the means among these 5 trials. So a kind of a way to calculate these means by hand before we do any model fitting is to just use the mean function. So if I were to do velocity, actually let's take a step back. So if I were to do trial num equals 1, what gets returned here? This is a bunch of true-false values. And it's true whenever trial num is 1. So that's the first, I believe, 20 measurements. And then it's false otherwise. It's false if the trial num is not equal to 1. So let me print out trial num as well. So the first 20 are 1s and the rest are not. So trial num equals 1 returns a vector that's the same length as trial num, and it's going to be true when trial num is 1 and it's false otherwise. Okay, that's good. Now what happens when you put a true-false vector as the argument, inside square brackets next to a variable? So this is a different vector velocity, but we're going to subset it with this all vector trial num equals 1. What this is going to do is it's going to pull out all of the all of the velocity values for which this is true. So what this is going to do is pull out all of the velocity values, so the first 20 velocity values, which are exactly the ones that correspond to the first trial number. So if I do this, if I run this, I get those. So those are the first 20 velocity values, which correspond to the first trial. And then now this is just a vector. So if I call mean on that vector, I'm just going to get the average of those values. So the average of the velocities for the first trial is 909. And then I can do this for all the other trials. I get 856 for 2, 845 for 3, 820 for 4, and 831 for 5. So we can see that the first trial has a sample average that's more than 50 larger than any of the other ones, and there's less spread among the other 4. So this is what we saw in the plot. Okay, so another way of doing that, there's a function in R called tapply, and there's actually a bunch of functions in R from what are called the apply family. You may have heard of lapply, sapply. Tapply is an interesting one. So you take in a vector. So what it does is it performs an operation on a vector, but it performs it separately for different levels of, or different values of another variable. So what do I mean by that? Let me just show you this example. So we're going to input the velocity vector, and let me skip this for a second. And the function we're going to apply is the mean function. So this takes the sample average, but we're going to apply it separately to each individual value of trial num. So the second argument means apply the third argument, apply the function and the third argument separately to each value of this variable on this variable. So what this is going to do is going to compute exactly this. So it computes mean of velocity, but on each separate value of trial num. So let's do that. So this is a sort of a one-line way to do what we did up here using the tapply function. And the output's kind of nice. It tells you what the individual value was. Actually, let's try this. If we do tapply velocity, and I'm just going to give it a different trial variable. So we had another one called trial fac, and fun equals mean. This should give the same answer, but it's going to give different labels because trial fac was a factor, so it has character labels. Trial fac ordered, yeah. This will put them in the right order: first, second, third, fourth, fifth. All right, so that's how to kind of do it by hand, but in practice, we're going to be using the LM function to fit models. So there's a really easy way to do this using LM, and it's going to give you a bunch of other additional information. So M1 is going to be our first attempt to use LM to estimate the means for each trial. And this first one, I'm deliberately giving you the wrong way to do it so you can see this mistake. So remember that trial num is a numeric variable. And whenever you do response tilde numeric variable, it's going to do a simple linear regression of the response on that variable, which is not the model that we want. So it's going to treat this trial num as numeric, and it's going to try to fit a line through the data. But what we really want is a factor model, which just has a separate mean or expected value for each level of the factor. So that's enough talking. Let me show you what this does. So that's LM. Here's the summary. You can see that instead of having 5 parameters here, it just has 2. It has an intercept and it has a slope, which should be your first clue that this is not the model that we want. So if I take the data and I plot it, I can actually put the line that's estimated by this model onto the plot. So the intercept is the first coefficient from M1. The slope is the second coefficient. I wonder why. I think I don't need this. Let me double check this. Yeah, that was a typo. I just need to put the intercept and the slope here. But somehow it still worked. It's kind of interesting. So this is not the model that we want. I'm just showing you that if you put in, even though trial num has 5 discrete values, it's a numeric variable. So R is going to think you want to do a simple linear regression. So it's going to fit a line to the data. So this is not what we want. What we really want is a separate average for each of the trial numbers. Okay, so the way to do that is to input the factor variable on the right side of the tilde. So if you do that, R will say, okay, this is a factor. I need to fit a factor model. So M2 is actually the model that we want. And let's do the summary. And so this has 5 coefficients. So this is your clue that this is probably the model that we want. Now let's go through and interpret these variables. So remember in R, actually let's take a step back. Remember with factor models, the model is over-parameterized. So whatever you fit the model, you have to impose some sort of constraint. And by default, what R does is it takes the coefficient, B1, that corresponds to the first level of the factor, and it sets that equal to 0. What that means is that you interpret the intercept, B0, as the estimate of the expected value for the first or baseline level of the factor. So the interpretation of this number is the estimate of the expected value for the first trial. And if we print out trial means, which is the thing we just calculated, this number, 909, matches this number. Okay, that's good. Now the interpretation of the other one, these are the estimates of the difference in expected value between the second trial and the first, the third trial in the first, the fourth trial in the first, and the fifth trial in the first. So what you'll notice is that these are all negative numbers, and that is exactly what we expect. And that's because the estimated means for the second through fifth trial are all smaller than the estimated mean for the first trial. So what this is telling you is that the second, third, fourth, and fifth trial, we estimate to have smaller means or expected values than the baseline trial, which is the first trial. Okay, that's good. And then there's more information here. There's a standard error for that difference, and a t-statistic, and a p-value. Now, like I said, this is the default in R. If you want to set a different level as the baseline, you'll have to re-level your factor. So let me, actually, let's do that real quick. So we can use, let's do summary, LM, velocity on trial fac. If you remember trial fac, we didn't do anything to the ordering of the level. So it did it alphabetically. So it treated the fifth trial as the baseline level. So before fitting it, let's guess what the intercept is going to be. So pause for a second. Maybe you can think about what the intercept is going to be. And it should be that the intercept is this number, 831.5, because that is the baseline level for this factor. So let's make sure. And yes, that is what it is. Now, as we discussed when we talked about constraints, the default one in R is not the only one. So one of the constraints we considered is setting B0 equal to 0. So there's a trick for doing that in R. It's to put in your factor variable here, but then do a -1. So -1 is the syntax to take out the intercept. And once you take out the intercept, then the model is no longer over-parameterized. So if we run that and look at the summary, now the numbers that show up are, this will be B1, B2, B3, B4, B5. And these, remember when we looked at that model, if you do the constraint that B0 equals 0, the interpretation of B1, B2, B3, B4, B5, or BJ, is the estimated expected value for the jth level of the factor. So here you just get back those means. So if we print those out just to show you, trial means, these numbers should match these numbers. Now you'll see the t-statistics are all wildly significant. So one thing to keep in mind is by default what R is doing is it's doing a hypothesis that the particular parameter is equal to 0. And you can see that these are all very different from 0 relative to the standard error. So you're going to get a very big t-statistic and a very small p-value. Now this is probably not a hypothesis that you're actually interested in. No one would hypothesize that the speed of light is 0. So this is not really all that meaningful in practice. All right, now let's do the Ftest. So if you'll notice, let's print out summary M2. So this is this model where we've set B1 equal to 0. So this is the estimated expected value for the first level, and these are the differences. If you'll notice at the very bottom of the output, it prints out an F statistic. So by default in R, it will do an Ftest, and the model, the models that it's comparing it's comparing this model, this whole thing, as the full model, and then the reduced model is a model with just the intercept in it. So R is doing that F statistic for you automatically. So the F statistic is this number, 4.288. The numerator degrees of freedom is 4. That's because the full model has 5 model degrees of freedom, and the reduced model just has an intercept, so it has 1 model degrees of freedom. 5 minus 1 is 4. And then the denominator degrees of freedom is 95. So this is n, which is 100, minus the full model degrees of freedom, which is 5. That's how you get 95. And the p-value for comparing these two models is 0.003. So which means we have reasonably strong evidence that the means are different among the 5 levels. So let's do this same Ftest by hand. The full model is M2. The reduced model is a model with just the intercept. So the assumption there is that all the expected values are the same among the 5 levels. So that I'm calling that M3. So that's the intercept model. I collect the residual sum of squares, the residual degrees of freedom, df0, and I can just print those out for you. Here, residual degrees of freedom for this intercept only model is 99, so 100 minus 1 model degrees of freedom. The full model, like I said, is M2. Here's the residual sum of squares, degrees of freedom, and I'll print those out. And then we'll just plug this in to the F statistic. So let me show you this. F stat should be 4.28. The p-value you can calculate like this with the pf function. Remember, we need to do 1 minus because by default this calculates the area under the curve beneath the F statistic. And we get 0.003 just like we got in this model output here. Okay, so again, that's how you do that Ftest by hand, but by default R will do that one for you. Okay, this is just checking those results. I'm not going to go through this in detail, but one thing you might want to do is to compare the means from every pair of these 5 levels of the factor. And there's a kind of an easy way to do that with a function in the Emmeans package. And the function, the package is called Emmeans, and so is the function, is also called Emmeans. You just put in the factor model, and you tell it which variable you want to do the comparisons on. So that's on the trial fact ordered. And then the pairs function will print out all those differences. So let me show you something real quick. So this line, for example, is first minus second. So this is comparing the average of the first trial to the second trial. Let me show you this summary again. That's exactly what this line is doing. It's doing second minus first, whereas this one is doing first minus second, but it's same thing. It's just the minus. So here you get a plus 53 instead of minus 53. Standard error is the same, 23.5. T statistic is 2.2. Same here, just a different sign. And the p-value is different. So this Emmean function must be doing an adjustment for multiple comparisons because you get a different p-value. All right, so we won't look too far into that, but if you want to do all these individual comparisons, you can do it with the Emmeans function. All right, so the last thing I want to show you is, if you recall the data, it looked like the first trial was different from the other 4, but the other 4, might not be all that different from each other. So one thing you might want to try is to say, I'm going to fit a model where the first trial has a different mean than the other 4, but the other 4 have the same mean. And I'm going to do a test to compare whether that model is any better than the reduced model where all the same, or whether the full model where you allow all 5 of them to be different is better than this simplified version. So I'm going to create a variable called last4. So this is either false or true if it's first trial or one of the last 4 trials. I'm going to convert it to a factor with as.factor. And then this model, what this is doing is it's a factor model where there's only 2 levels of the factor. It's either false if it's from the last 4, which is 2, 3, 4, 5, or it's true if it's not from the last 4, namely if it's from the, sorry, I got that backwards. It's true if it is from the last 4, that's why it's called last 4, and it's false if it's not from the last 4, which namely it's the first trial. So this is a factor model. The baseline level is false because false is alphabetized before true. So this is the intercept corresponds to the expected value for the false level of the factor, which is level 1. And then it's true for the other one. So what this is saying is that on average, the last 4 trials have an expected value that's 70.75 lower than the first trial. Okay, so we're going to use the ANOVA function to compare these models. If you recall, so this is the most reduced model. This M3 is the model that has the same mean across the 5 trials. This M4 that we just fit is kind of an intermediate. It allows the mean of the first trial to be different from the last 4, but it requires the means of the last 4 all to be the same. And then the most flexible model we fit was M2, which allows a different mean in each of the 5 trials. So I'm going to skip this because I prefer to use the ANOVA function with 2 models in it. So if you do ANOVA M3, M2, this is going to compare the constant mean model to the model, the full factor model, full 1 factor model. And this, you should recall, this is the p-value. We already did that comparison. That's the p-value you get. Now we can do other comparisons with this intermediate model. So M3, M4 compares the constant mean model to a model with equal means among the last 4 trials. We get an even smaller p-value. And then we can compare this model with a constant mean among the last 4 to the full model, where every trial is allowed to have a different expected value. And here we actually don't get a rejection. So take a step back. What this is saying is that we don't have enough evidence. So we do have enough evidence to say that the first trial is different from the last 4, but we don't have enough evidence to say that all the means are all the means are different relative to a model where you allow the first one to be different, but the last 4 have to be the same. We don't have enough evidence to reject that model in favor of a model where all the means are different. And then you actually can string together multiple models, and this really only makes sense if the first one is nested inside the second and the second is nested inside the third. But you can do this comparison, and this will print out both of those Ftests for you. Okay, so that's the end of the video. There is more information in this R script. So it's going to look at the matrix version of everything. So it shows you what these dummy variables are. So that's going to be stored in this matrix X. And then shows you how to use the variance covariance matrix to do what this Emmeans function did.